Welcome back to geometry. We want to take a look at section 17 still. So let's return back to our notes. We want to talk about several theorems for quadrilaterals. This first set of theorems that we're going to take a look at, we will not prove. We'll follow this up though with a collection to theorems that we will prove. All right, so the first one, theorem 17.2, the angle sum theorem for quadrilaterals. So the sum of the measures of the interior angles of a convex, right, we still want convex quadrilateral is what? Well, for any four-sided figure, what is the sum of the interior angles? Well, of course, that's 360 degrees. Notice here that we don't give a proof, and it doesn't say that it's part of the exercises, but still you should be able to prove this. So can you prove this? The answer to that question should be yes. So if you're unsure, you can certainly refer back to section 3 where we first discussed polygons, and I think you'll get a pretty clear indication of how it can be proven from that section. All right, so our favorite kind of quadrilateral is a parallelogram. There's quite a bit that we can say about them. It may not be your actual favorite, and that's okay, I'll forgive you for that, but we have several properties for parallelograms. A quadrilateral is a parallelogram if and only if it meets one of these conditions. So if we have one, doesn't matter which one, if we have one condition, we can conclude that the quadrilateral is a parallelogram. And if we have a parallelogram, then we can conclude any one of these conditions. So for, again, any one of these will give parallelogram, and parallelogram will give any one of these that you like. And what are the conditions? Well, let's say we have a parallelogram. Let's try and write this out here. So let's consider 4 vertices, A, B, C, and D. And because we can, let's go ahead and place the parallelogram there. So it should look something like a parallelogram. That looks pretty good. All right. So here we have our parallelogram, or a quadrilateral, I guess. And our quadrilateral is a parallelogram if and only if the triangle made by A, B, and C, that is A, B, C, so this triangle is congruent to, okay, so we want to make sure that we carefully say our congruence here. So we would expect this triangle to be congruent to the other half, but we should name it in the same way. So for example, the side from A to B is congruent to the side from C to D. So we do our short side AB, and then our, not our longest, but our middle length side from B to C. So we should do CD and then DA. So triangle CDA. Excellent. So if those two triangles are congruent, then we have a parallelogram. All right. If we have that both pairs of opposite sides are congruent, then it's a parallelogram. And it's a parallelogram, or if it's a parallelogram, then both pairs of opposite sides are congruent. Remember, the parallelogram is defined to be 2 pairs of parallel lines. So parallelogram is defined by 2 pairs of parallel lines. So if we want to say that we have opposite sides that are congruent, both pairs of opposite sides are congruent, we cannot cite the definition of a parallelogram. Rather, we would have to cite this theorem since it is a parallelogram, okay, for example. So again, when you're writing a proof, if you want to say that both pairs of opposite sides are congruent, you would first have to say you'd have to say that by theorem 17.3, not by the definition. All right, so the diagonals, that is from A to C and from B to D, the diagonals bisect each other. So where they meet is the midpoint of each of those line segments. All right, both pairs of opposite angles are congruent. Notice that one pair of opposite angles is being congruent is not sufficient. We have to have that both are. For example, a kite also has a pair of opposite angles that are congruent, but it is not a parallelogram. And then the last would be a pair of opposite sides are parallel, but that's certainly not enough because a trapezoid satisfies that. We also need it to be congruent. So a pair of opposite sides are parallel and congruent. That is sufficient to give us a parallelogram as well. Excellent. So for the proof of this theorem 17.3, what we have is actually an activity. And the goal is for you to take 5 sheets of paper and staple them all right down the middle. That will give you a booklet with 5 folds, okay, 5 openings. And on one side of each of these pairs of pages, you should prove the forward direction, and on the other side, you should prove the backwards direction. So that is an activity for you guys to do, and it is part of the homework for this section. So feel free to read this, and if you have any questions, let me know. All right, so the next theorem is the rectangle parallelogram theorem. Of course, a rectangle is a parallelogram. And under what conditions is a parallelogram a rectangle? Well, only when it has a right angle. So a parallelogram with a right angle, right? We only need it to have one right angle. As soon as it has one, we know the opposite corner, the opposite angle is also a right angle. And then, let's see here, then we would have, let's see, I'm thinking we can use perpendiculars. Yep. I believe parallel perpendiculars or perpendicular parallels theorem. Well, one of those two anyway. So once we have one right angle, we can identify that all of them are right angles. So a parallelogram with a right angle is a rectangle. Excellent. The proof of this is an exercise. So there you go. I just talked about how you can prove it as well. All right. A rhombus, right? A rhombus looks something like this, and a rhombus is a parallelogram. But it is also a kite. If you don't recall what a parallelogram is, a kite is, a rhombus is, I believe we talk about these things in section 3, but of course, you could quickly search on the internet what the definitions are for each of these things as well. A square is many things, right? It is a rectangle. A square is a rhombus. A square is a kite. And of course, it is a parallelogram as well. for a kite, right, this would be something like, I believe for a kite it is defined to be two pairs of adjacent congruent sides. So these two sides are congruent, they're adjacent, and these two sides are congruent, they're adjacent. So the kite is defined to be two pairs of congruent sides. And when we have such a case as a kite, then the diagonals are perpendicular to one another. Excellent. And then the diagonals of a rhombus, well, we said a rhombus is a parallelogram and a kite. So we know that they are perpendicular because it's a kite. But because it's a parallelogram, see if we can scroll back up here, the diagonals bisect each other in a parallelogram. So we have that they bisect each other and that they're perpendicular. So the diagonals of a rhombus are perpendicular bisectors. Perpendicular bisectors of each other. Excellent. From here, we'll take a look at two more theorems, but for the remaining theorems, we will consider the proofs, or at least partial proofs of both of them. So for now, have a great day, and I'll see you back here shortly to take a look at those remaining theorems.